everybody. I am Ben Linsay, and this is HyperLogLog, the analysis of a near-optimal cardinality estimation algorithm. So I'm here talking about this paper because I have a pretty personal relationship with this paper. I got into this paper way back when, while I was starting my career in tech. It got me into doing all kinds of cool things with streaming data, and it also got me into reading papers and showing up to meetups like this. So I'm here because of this paper, in more than one way. So we're going to go through why would you bother. We're going to talk about the intuition behind this algorithm. We're going to do a second round. We're going to talk about the algorithm itself and all the gory details. We're going to talk about some cool consequences of the way it works. And then we're going to talk about what it looks like to actually put one of these things in production. So let's start at the start and figure out why we would bother doing this. Right? So this paper is about estimating the cardinality of a multiset. Cardinality is a big math word for size. And multiset just means what we're trying to do is we're trying to figure out how many things are in a set, but we're allowed to see elements of the same set multiple times, right? However many times you repeat an element, it shouldn't affect our guess as to like how big the size of this set is. So the authors point out that you can do this exactly. But to do it exactly, you need to store basically something for every element in your set, right? Not for everything in your data stream, but for everything in the final size of the set that you're trying to estimate. So this paper is about trying to get around that requirement, right? What happens if you've got a set and the final set itself doesn't fit in RAM on the device you're using, or it doesn't even fit in disk maybe, or you've only got space given that this thing doesn't fit in RAM or on disk, you've got a stream of elements and you're allowed to go through it once, right? Here's a really cheesy Ruby example, just to sort of like warm us up, sort of make the problem seem right. We're going through 1 billion elements here, but since we're picking random integers between 0 and 2, that's what rand does in Ruby if you give it 3. This set we're picking, right, it's only ever going to have size 3. We can change that to 30,000 just by changing what we pass to rand. But if we just stop picking random numbers and we start passing the whole thing through, right, the size of that set at the bottom, to call length, we're going to have to put 1 billion integers into a Ruby set. 32-bit integers, if you do 1 billion of them, that's like a couple gigs of memory, and like who knows what overhead our runtime is going to add here. So we can already get a sense for like, all right, maybe this isn't practical. The authors cite real reasons you would actually want to do something like this and jam way too many elements into a set. Their example is network traffic, right? Suppose you're listening on a network and you're looking at all unique source destination address pairs that you can see on that network, right? They claim that there's some research that lets you say like, all right, if suddenly you start seeing a lot more of those connection pairs, there's something funny going on. There's like a DDoS in progress, or there's a worm trying to propagate across your network. So if you see the number of connections double from what you normally see, right, like that's a problem. But maybe the only place you can see the whole network is on a router. It's a small device. So suddenly there's no way to keep all of those address pairs in memory. Where I found this paper was while working in ad tech. So in ad tech, you have a slightly different problem, but you still end up not being able to keep all your sets in memory, right? In ad tech, a lot of the time what you do is you want to track unique users who saw a particular ad on a particular page at a particular time. And you also want to track all of that like per some like unique attributes about these users. So, you have small-ish sets, right? You have thousands or tens of thousands of unique user IDs, but you're going to have tens of thousands of these sets, so all of a sudden you're keeping a ton of data in memory again. So if you can do something to shrink that way down, right, your life gets a lot easier. Unlike our network example, right, where you're looking for doubling of the size of your set, in advertising, you really don't care if 12,000 people or 12,103 saw an ad, right? They're functionally equivalent to you. So here's where we're going to end up with this paper, right? We're going to have some set-like thing. It's going to have some state. We'll figure out what that is as we go through the paper. We're going to be able to add an element to it, and we're going to be able to query it just to get the cardinality out. We're not going to be able to do anything else. We're not going to be able to test membership. We're not going to be able to do intersections. So what the authors promise us is that with this data structure, we're going to be able to estimate well beyond 1 billion elements. We're going to be within about 2% accuracy, and we're only going to use 1.5K. Just for context, right, those billion integers we talked about was a gig. This is a huge memory savings, right? We're like multiple orders of magnitude off of what we would require to do this explicitly. So, you know, to me, that seems like a good trade-off. And in a little more detail, what you end up finding out when you read this paper is that for some set with fixed cardinality n, right, we get to pick some small m, and we get to use memory proportional to that small m we picked that has nothing to do with the size of the set. Our error is proportional to that m we pick, right? So we've got this slider where we can trade off memory for error. And we're going to have constant time adds, right? We're not going to trade anything else to do this. All we're trading is that accuracy cost for this space saving. So before we get too far into this, I want to give a little bit of a disclaimer. We're skipping all the proofs in this paper. The proofs in this paper involve techniques that are now standard in the analysis of algorithms, like Poissonization of Mellin transforms and saddle point depoissonization. I don't know what that means either. It's grad school level, like postdoc level complex analysis and statistics, and I don't have either of those degrees. It's a wonderful paper, even if you read around the proofs. You can get almost all of what you need to implement this thing. And if you do want to implement this thing, you don't really have to dive too deep into why the proofs work. The authors do a really good job of pointing out the spots you need to go look at to find the constants you're looking for or whatever. The downside, really the only downside, is we're not going to be able to justify why certain things are what they are. We're just going to have to accept that statistics and math works. I'm okay with that. So let's get into the intuition for why this thing works and how it works. Imagine I'm sitting here and I'm just flipping a coin forever, right? All I'm going to do is track how many tails I've gotten in a row. And I'm just going to, every time I get a long run of tails, I'm going to remember that, and I'm only going to remember the longest run of tails I get. So if you come up and you ask me anything, the only thing I'll tell you is what the longest run of tails I've had so far is. And if you want to figure out how long I've been here, that gives you an okay way to make a guess, right? If I've got a short run of tails, it probably hasn't been that long, it's been a couple minutes, but if I tell you I hit like 50 tails in a row, you're gonna be like, dude, why have you been doing this for so long? So if we had a little bit of structure to this, right? And instead of flipping the coin forever, I'm gonna flip it 32 times. And now I'm only gonna track the runs of tails I get at sort of the beginning of those 32 flips. That makes your life easier, right? It's a little bit easier to figure out the probability of those runs of tails. You can ignore certain things that look weird, and you can start to write down what this all looks like. So, the probability that on any given 32 flip experiment that I get no tails is a half, that I don't start with tails is a half. Probability that I get 1 tails at the beginning is a fourth, and so on, right? So the probability that my run of 32 flips starts with n tails is 1/2 to the n. So at this point, right, I'm still keeping track of the longest one of these things I'm doing. I'm not keeping track of every experiment for you. I'm keeping track of the longest run at the beginning of 32 flips I've gotten. You can make this guess, right? If I tell you the longest run is x, the only guess you're really justified in making is that I've been doing this at least 2 to the x times, right? And that comes from these probabilities we've got. So you might not be super surprised if I tell you that nothing changes if instead of flipping a coin, I'm randomly setting the bits in a 32-bit integer. And instead of tracking tails, I'm tracking the longest run of zeros at the beginning of a 32-bit integer. The authors of the paper talk about this as a bit pattern observable. And so this paper is based around looking at bit pattern observables in streams of random integers. The observable, well, that's a tongue twister. The observable that they use for HLL is this function called row of x. It's the position of the leftmost 1 bit in any binary string. And by total coincidence, it happens to be almost exactly the longest run of leading zeros, the beginning of a binary string, right? So if we've got 2 leading zeros, our row function is 3. If we've got 4 leading zeros, it's 5. 7 leading zeros, it's 8, right? We're off by 1. So we can update our guess, right? We can say that given this random stream of elements, if x is the max of row across all these 32-bit integers we've seen, right? There are probably at least 2 to the x experiments, 2 to the x distinct things in this stream so far. So we've got 2 problems right now, right? The first problem is that we're trying to estimate the size of any old set of any old things. This only works when we've got things that look like that coin flip experiment, right? Every bit has to have an equal probability of being 1 or 0. All those probabilities have to be independent of each other. Your string IDs don't look like that, right? We're going to set that one aside for a few minutes and come back to it. It's a solvable problem, I promise. The second problem we have, right, is that this is still a really shitty guess. We're only guessing powers of 2. There's a lot of space between powers of 2 as those powers get big, right? So if your actual value is somewhere in the middle, your error is going to be real high. This paper comes in with a cool answer. Turns out you can do a bunch of crappy experiments, and you can average them together, and you can shrink the mean, or you can shrink the standard deviation based on how many of these crappy experiments you do, right? As long as these experiments are independent of each other, you can take the standard deviation of the original, that's this sigma here in this quote, right? And you can divide by the square root of m. So if you do a whole bunch of experiments, we can basically drive our error down as low as we want. The bad news, right, it's a square root. It flattens out over time, so there's like diminishing returns on every experiment we add. But we can just keep adding more as long as they're cheap and keep driving this error down and down and down. And that's basically the big picture for how this is going to work, right? We're going to do parallel experiments on this stream of data. We're going to get bad estimators. And we're going to combine all of those bad estimators to get our final good cardinality estimate. Easy peasy. So let's get into the details. Let's talk about add first. Add's going to tell us how add works, and it's also going to make it clear like what the state of this data structure needs to be. So like I was talking about, right? We've got our stream of input data. Maybe it's random IDs, maybe it's this very cool input data I've got up here, and we need to make it look random, right? This does not look random, even if you're picking random strings, right? There's structure to text. There's structure to probably all data you care about finding the size of a set. So we have to be able to make this look random, right? So hash functions exist, which is great for us, because hash functions make things look random. Turns out that's one of the weakest guarantees you can put on a hash function. Uniform hash functions are pretty common. You can ask a lot more of your hash function, like a cryptographic hash function is a really good example of something that looks random and also guarantees you a whole bunch of other things that I'm not going to talk about, because I don't really know what I'm talking about there. But it means that, you know, in the setting of HLL, it's really easy and really possible to go pick out a really good, really fast hash function that gets you really uniformly distributed data that, you know, looks like these random experiments. For whatever reason, Murmur3 tends to be a really popular one these days. It's good, it's fast, it's really uniform. So if you're curious what a uniform but not cryptographic hash function looks like, there you go. All right, so we've got random coin flip looking experiments, and now we need to do a bunch of them in parallel. So the authors of the paper point out that the most obvious thing you can do is find a bunch of different hash functions, right? Every time our string comes in, we're going to hash it m different ways, and we're going to take this bit pattern observable across all of those hashed values. Turns out that's not really a practical thing to do, because finding m independent hash functions is an open problem in computer science. So we're not doing this one. Instead, what we're going to do is we're going to fake it. It's an approximation algorithm, so let's just wing it, right? What we're going to do is we're going to emulate the effect by dividing the input stream into substreams. That sounds a little strange, so we're just going to go through a quick example. If you've got the string A coming in, you hash it. Somehow you decide it needs to go into substream 2. Just quick note. The authors use the notation of having each substream called big M, but they pick little m of them. So if the m's get ambiguous, I'm sorry, it's not my fault. They also call the substreams registers. They sort of switch interchangeably at some point in the paper. So if I start saying register, I mean substream. All right, so we've got A, it's going to the second substream. We've got B, for whatever reason, it's going to the last substream. The only important bit is that we're sending A back to the second substream next time we see it, right? What they mean by splitting into substreams is basically like we're partitioning the final input set. We're partitioning all our elements, and hopefully we're doing it pretty uniformly across all of our substreams. All right, so with that in hand, we can just look at the actual add. This is it, this is the whole thing. It's pretty dense though, so we're gonna walk through it line by line. So what we're going to do, we're going to hash our input value, and we're going to get out this binary string. We're going to lop off the leftmost bits. Those are those bits in blue, and we're going to use that as the index to pick the substream we're going to. We're going to take the remaining bits, those bits in orange, and we're going to calculate that bit pattern observable over all of them. And then we're going to use that index to pick the right substream, and we're just going to keep the max of that row we calculated with whatever the value was before, right? There was a shouted question. The question was, what's m, m underscore I. I got caught. I mixed my notation. M underscore I should be the same as m bracket I. It's just the ith substream. So I want to point out at this point that this is all really fast. We are keeping our promise of constant time updates. We're taking a hash of whatever our input data is. We're doing a couple bit shifts. We're finding the leftmost one, which is like, it's an LLVM intrinsic. I assume that's like a single CPU instruction in a lot of places. And then we're taking a max, right? Like, this is all stuff modern CPUs are really good at. So we are definitely not paying a ton of performance cost here. And it turns out that all the data we need to keep around is just the value of these running maxes, right? Max row for every substream. So our HLL is just going to look like an array of these max values. So with that in hand, we can talk about how we're going to turn that array into our cardinality estimate. Like we mentioned before, and we were talking about how the intuition for all of this, right? We're going to take each one of those estimators, and we're going to take the mean, and we're going to get all of those bad estimators together to make a good estimator. Right? So let's just restate the obvious. This HLL is this array of max row values. So taking our estimate, we're taking a mean over 2 to all those row values, because way back when we said that each one of our guesses, right, if we had seen a run of length x, our best guess was 2 to the x. The only catch here is we're not actually taking a mean. They tell you in the paper that they're using what's called a harmonic mean, and they also very nicely drop the hint that this isn't actually their first attempt at doing this. Turns out the authors of this paper had also written a paper just called LogLog a few years earlier. That paper tried to combine all these estimates into a good estimator by using the geometric mean. There ended up being some problems with that. You would get all kinds of crazy variance. It was really hard to get tight bounds on the error. So they tried a bunch of manual corrections at certain points, and like, you know, if one of your estimators was way different than all the others, correct in this certain way. They called those corrections super LogLog, and now they're back at it for a third time. We're trying the harmonic mean out this time, and that's how we got to HyperLogLog, because once you're out of the regular and the super version, I guess you gotta go to hyper. Okay, so what's a harmonic mean and why does it help? So the harmonic mean is one of the 3 Pythagorean means. It's the arithmetic mean, the geometric mean, and the harmonic mean. And if you go look the Pythagorean means up, you end up on MathWorld or on Wikipedia, and you get this picture which gets us back to feeling like this. The harmonic mean looks a lot like the arithmetic mean. You just raise everything to the power -1. I guess there's a lot you can end up saying about the harmonic mean and its geometric interpretation, but I guess what really ends up mattering is that the way the arithmetic mean tends to overrepresent large outliers, the harmonic mean tends to overrepresent small outliers. So I think naturally it ends up smoothing out all of those errors they tried to tame by hand with super LogLog. And that's all we got to know for our evaluation function. We end up at this intimidating, weird-looking thing, but I promise it makes some amount of sense. So we're going to go right to left and talk about what these different parts are. So on the right, we've got the harmonic mean of all of our bad estimators, right? We decided earlier that our our estimates were all 2 to the x, right? So this is 2 to the minus register value for all of these. Again, because the harmonic mean is the sum of 1 over everything. And that's that whole weird looking orange section, right? There's nothing else to it. This a to the m in the middle is a bias correction function. It's a function of how many sub-experiments we've got. So you can end up treating it like a constant, which is great. It comes from a really gross indefinite integral somewhere deep in the proofs. But the good news is the authors are just like, nobody wants this. Here's a lookup table. So here are a lot of the common values of m you're going to use. Here's how to compute a of m. Finally, the most interesting part of this whole estimator to me is this last little m hanging out by itself on the left. Remember, we partitioned our set into substreams, right? So what we're actually doing with each of our bad estimators is estimating the size of one of these partitions. But since there are m of them, each one is going to be estimating 1 over m times the actual size of the set we're after. Because there should be 1 over m elements in each partition if we partitioned randomly. So we have to multiply again by m to get back to the size of the actual set. And that's it. That's our estimate. We made it. So I'll take a deep breath. And let's recap, right? So we had our add function, which basically just hashes the input, partitions it into those substreams, and keeps the max row of x per substream. Cardinality, we're just grabbing all those substream estimates. We're taking the harmonic mean, and we're correcting for bias. And hopefully, I've convinced you now that we've arrived back at the promises we got at the beginning, right? We've got some m we picked independent of the size of our set. We're using memory, right? We're doing m sub-experiments that we have to keep a max for. We're using OM memory. We have constant time to add an element. And there's no way I've convinced you that the standard error thing is real, but that's what it is. The authors, so the details of why the standard error thing, or why the standard error is 1 over square root of m, show up deep in the proof section. And when you do eventually scan your eyes over the proof section, you'll notice this annoying little caveat. So standard error is tightly bounded here as our estimate goes to infinity. That's sort of annoying, right? Like, we don't actually know that this is a good estimate until our set gets infinitely large. The authors are equally annoyed by that. So they give up on the math, and they do a lot of simulation work to figure out exactly where those bounds start to kick in, exactly where 1.04 over the square root of m looks like the actual error of this algorithm. And they introduce what they call the small range correction. So basically, what they figure out is that in the range where before the bounds start getting tight, you tend not to have every sub-experiment, sorry, you tend to not have put a value in every sub-experiment yet, right? Like some of those substreams are still going to be empty. What's nice is that if you've taken much statistics at all, you've run into something called the birthday problem. Turns out this totally tracks with that, and you can do some pretty cool statistics to get a really nice estimate just based on the number of elements you, excuse me. You can do some really nice statistics to get an estimate just based on the number of substreams you've put an element into. That's got really nice error bounds. And the authors are like, hey, if your estimate is smaller than this, use the small range correction. If not, you're good with the regular estimator. They also point out the interesting subtlety that what HLL is actually estimating is not the distinct number of elements in your set, it's the distinct number of hashed values in your input stream, right? We talked about hashing as like a really important part of that add function. It turns out it's sort of like a weird externality to this, just to get us in the right world where we can do an estimate like this. But they're sympathetic. What they tell you is that once your estimator gets really large, once you're approaching to the 32, it's really highly likely that you've got hash collisions going on. So they give you another little correction you can make to try to correct from estimating the number of distinct hashed values you've gotten back to the number of actual values in your set. What's neat is that this again uses like birthday paradox, also called balls and bins math. So there's this really nice symmetry between the small range and the large range, which you can see. Shit, do I have the pointer? All right, I'm just gonna jump and point. So this is the final algorithm, and it's exactly what we talked about, right? So if you can see this for V and M up here, that's just for every element in the substream. Everything above it's initialization, it's those constants we can just take on faith. But we're gonna hash our input stream. We're gonna grab those first B bits. We're gonna grab the rest of the bits, and then we're gonna set this mth substream to the max of what it was before, and that row function of this W bits. That's the add function we talked about. The estimate looks almost exactly what I had on those slides. We got the sum of 2 to the minus register values, 1 over that. We're multiplying by the m. I pulled the extra m out on the slides so we could talk about it. And we've got that alpha that comes from all the way up at the top, which is solving that indefinite integral. And then you can see this neat symmetry down here where you've got the small range and the large range corrections. And in the middle, you've just got, use your actual estimate. Cool, we did it. Let's talk about all the weird, good, unintended consequences of all this. I'll take them at the end. I'll talk at the end. So the first cool consequence is we can talk about where the LogLog in HyperLogLog comes from, right? On add, right, we're taking this input string of bits, we're lopping off the first B, and we're using the remaining orange bits to calculate our observable function, right? So the maximum value that that observable function can have is 32 minus B, right? If you only got 32 bits and you get rid of B of them, we only have those remaining bits. We can only have a run as long as the number of bits we have. So that means for each observable, all we have to do is store an int less than or equal to 32, right? If we pick no partitions, we put this all in one stream and accept a really bad estimator, that will have 32 orange bits. So, that observable can be 32. So again, our storage is all we got to do for each experiment is store an int less than 32. Log base 2 of 32 is 5, so we can store that int in 5 bits, which gets us to the fact that all we need to do to store each experiment is store log 2 of 2 to the 32 bits. And I think at this point, you can squint and you can see that the space complexity of this algorithm is now O of log 2 of the maximum possible size of this set. So that's how we get to the LogLog. We got the hyper, we did it. We got both halves. We talked about space complexity. We can talk about the actual size of these things now that we know that each register only needs to be 5 bits. So the total size of an HLL is just the number of registers times the size of each register. And we've talked about our standard error, 1.04 divided by the square root of m. So if we pick if we decide we're going to have 2 to the 11 experiments, we got 5 bits. This whole thing fits in 1280 bytes, and our standard error is 0.023-ish. That's the estimate you get in the abstract of the paper, where they say, with a typical accuracy of 2%, we can get within 1.5K. They're underselling themselves. That's pretty cool. So if you do add a table for a lot of common values of m, you can sort of get more of a sense for the trade-off, right? The error we're getting is the standard error. So 99% of the time we'll be within 3 times the standard error. I wrote it out so you don't have to do the math in your head. Yeah, and so you can sort of get a sense here, right? If we're really tight on space, we can fit this whole thing in 640 bytes, and we'll be within 10%, 99% of the time. But if we really care about accuracy, we can go up to 1%, 99% of the time, and stay within 40 kilobytes. What's really impressive to me is comparing this to the size of an actual set. So with 640 bytes, you get 160 32-bit ints. Your HLL goes up to 2 to the 32 minus 1. Your set goes up to 160. And as you dial this up, the sets don't really get that big, right? Like for 1% error, the most you could do explicitly is about 10K elements, right? And with an HLL, you're still going to 2 to the 32 minus 1. So another cool consequence of the way this algorithm ends up working is buried in maybe the cheekiest footnote I've ever seen. This footnote is on one of the final sentences in the paper, where they just casually toss out that this algorithm is easy to parallelize. So this is the full footnote. Given an arbitrary partitioning of the original file into subfiles, it suffices to collect register values and imply component-wise a max operation. I don't know why we're talking about files. This is also the first time the word files appears in the paper. But basically what this means is you can just arbitrarily split your input data, right? We're not partitioning the way we were in the add function. We're splitting it. We don't care. What we can do is we can pipe each half into 2 separate HLLs, and then we can take the max of every corresponding register, and that gets us one HLL that is the same as if we had piped all of the data into it in the first place. So in other words, you can take the union of 2 sets in an HLL, right? You can union 2 HLLs. It really truly does mean that the union of HLL of A and B is exactly the same as the HLL of the union of A and B, right? You're not doing a really cheeky, janky thing where you're trying to add unique counts. If you're somebody who's lived in an Excel spreadsheet before and accidentally done this and cursed a lot, you can appreciate how cool this is. But this ends up being true basically just because max is an associative function, right? I think you can convince yourself that it doesn't matter what order you take the max of all your elements in, you're still going to end up with the same result. So if we take the max of the first register of 2 HLLs, that's the same as if we had taken the max of all of the elements in the stream individually, which is great. So now we've got the super useful data structure, and we've got this cool third function on it. This ends up being like immensely practical. You can imagine having roll-up counts of unique users in your SQL database somewhere, and instead of having unique counts, if you have an HLL, you can do things like, hey, I need to know how many unique users showed up between 3 and 5 a.m. on every third Tuesday of the month for the last 3 years. If you're not keeping something like this, somebody goes and writes a Hadoop job over all your logs in cold storage. If you are using HLLs, you get the answer in like 10 seconds. Which is a great segue into how people actually use this in real life. This is a little bit of a cop-out. I'm not actually going to show you an implementation or anything. We're going to talk about a second paper. So 2013, Google puts out a paper about all of the adaptations that they made to the original algorithm to run this in production. They're all pretty cool, and they all address things I'm sure that would have been questions otherwise. So the first thing they talk about is switching to 64-bit hash functions. We got a lot of data. It's 2018 now. Data just keeps getting bigger. 2 to the 32 isn't actually that big. 2 to the 32 is about 4 billion, and the way we get our large range correction, it kicks in around 145 million elements. That's not great. You're getting a lot of bias in your error for no reason a lot of the time. Google would like to really have the tighter error bounds that come with a regular estimate and not the looser ones that come with this large range estimator. So they switch to 64-bit hash functions and decide that with 64-bit hash functions, hash collisions just aren't going to be a problem for them. And they sort of also say that if they are, fuck it, they're going to go to 128-bit hash functions. They don't want to deal. The first consequence of this is you got to pick a hash function good enough to give you 64 bits of randomness. That's really not a problem these days. The second consequence, remember we talked about how we need log2 of 32 bits to store each register. Unfortunately, we've upgraded from 5 to 6 bits, which means we've inflated our storage space for this thing by 20%. It's a really okay sell for me to do that. We're going from like 1.5K to 1.8K. I'm cool. It still seems like a good trade-off if you need to make it. The next thing they really get into, we've ditched that large range correction. Next up is that small range correction. Again, they really don't like the extra error and the extra bias that comes with those corrections. Unfortunately, there's no brute force thing you can do for the small range the way you can switch to 64-bit hash functions for the large range. So what Google does is a different kind of brute force. They run a whole bunch of simulations and build a large lookup table to correct for your bias and for your error all across that small range for every M you want to pick. So their implementations ship with this table, and instead of doing that small range correction, you go look for yet another constant, and you fix your answer. It's really unglamorous, but there are really good graphs in the paper that convince you that, like, damn, this was a good idea. And finally, they give us this like alternate data structure representation that you might want to end up using for HLLs. So remember, we've got our array of substreams, our array of estimators. And as you're building this thing up, especially if you're not putting data in it very frequently, you can imagine that most of those are empty most of the time, right? So you've got a big array, you got most of the elements you don't care about. It starts to look a lot like, something like a map. So they build a pretty cool compressed integer specific hash map that they use for HLLs, as they have very, very, very few elements in them. And that saves them apparently a ton of space in production. It's really dope. A lot of the open source implementations don't include this because you tend to, depending on your use case, you often rocket right by that super small range. So it's a lot of work for not a lot of payoff for a lot of people. But for Google, apparently this pays huge dividends. And so that's it. There's so much more you could say, but I'm already starting to run a little long. I got some good links in here. I used to work at this company called Aggregate Knowledge. That's where I met this paper. We have a bunch of good blog posts up on this. I'll put these slides up so you can go click on these links later. We have a bunch of good blog posts on this. We open sourced an implementation. We actually open sourced 3 implementations. We did a Postgres one, a Java one, and a JavaScript one. And they're all data format compatible with each other. So you can generate your HLs in Java, move them between your database and your front end. It's awesome, it's great. There's one in Algebird, which is Twitter's big data stuff. And Lucene even ships with one, so they're everywhere. All good implementations, all worth reading. And finally, if you've got questions and you don't find me here, I'm on Twitter and would love to talk to you about all this stuff. That's it. Thank you.